I know.
All right, welcome back. Second day of section 1.1. Hopefully the only other day of section 1.1. I'll just let you guys know right now. You will have a work day on Monday over the section 1.1 homework because I have to finish. I have to do what I'm going to do with you guys today with my second period class. I'm going to have to do this on Monday. So this homework is going to be due on Tuesday. I have not changed. I don't know if I changed the due date yet in Canvas, but I will change the due date in Canvas to Tuesday. Okay, so this will be due on Tuesday of next week. Sound good? I know you guys kind of get the better end of the deal, but all right. So section 1.1. Oh, get back down there. Section 1.1 was all about different ways that we talk about functions and why we need functions, right? Functions are just ways to demonstrate or to model real life situations, and we can talk about them in a variety of different ways. We can talk about them, verbally, numerically, visually, algebraically, all sorts of different ways we can talk about functions. And what we're really going to do in calculus is kind of tie all of those together and talk about them in different ways to really kind of wrap our minds around the different way how a function acts and how we can work with it. So we did this bear of a problem yesterday, the one with the cost. So let's get to this. Find the domain of each function. I'm not asked to graph here. All I'm asked to do is just find the domain. Again, just reviewing topics that you probably should know how to do, just kind of dusting off the cobwebs a little bit, making sure that we know how to find domains and how to state domains and the weird things that could happen here. So what's weird about the domain of a square root function? What can't happen in a square root function? What can't happen? Can you square root a negative and it become a real number? No, you cannot square root a negative number. Can you square root 0? Yes, the square root of 0 is 0, but you cannot square root any negative number. So what you're looking at with a square root function, and this is only ever in even root functions, so like square, fourth root, sixth root, even root functions. Odd root functions, that's a little bit different. You can have an odd root of a negative number. But even rooted functions, you cannot have negatives underneath the radical. So you basically have to say this, x plus 2 has to be greater than or equal to 0, right? X plus 2 has to be greater than or equal to 0, so we would say x has to be greater than or equal to -2. So there's our rule for it. You know, that's not really a proper way to write a domain. I guess if you wanted to go so far as to put it in like some sort of set builder notation, I guess you could do that, right? But I like to use interval notation. So let's use x is greater than or equal to -2. Let's put that into interval notation. Greater than or equal to -2. So still equal to -2, but any other big number bigger than -2, right? So -2 to infinity. Remember, you always put a parenthesis on infinity. You never bracket infinity. And that's how we represent greater than or equal to -2. Okay, so we got the domain there. What about example B here? G of x is 1 over x squared minus x. This is a rational function, right? And we know it's rational because we see an x in the denominator. Right? We see a fraction function where x is in the denominator. What can't happen here? Or what do we have to be careful of? Dividing by 0, right? The denominator just cannot be 0. So to figure out what's going to happen here, I'm just going to say x squared minus x cannot be 0. Let's solve that equation. Or that inequality, I guess we should say, because it cannot be equal to 0. All right, well, factor out an x. Okay, so that means x cannot be 0. X minus 1 cannot be 0. So x cannot be 0 and x cannot be 1. So those are the two values. That's where everything else will exist. 0 will not exist and 1 will not exist. So 0 and 1 are the only things out of my domain that I kind of have to get out of there. This one would actually be easier to write in some sort of set builder notation. We could say the set of all numbers x such that x is non-zero and then x is not 1. Done. That's kind of the easiest way to write that one. But again, I like interval notation. This one's, harder to write in interval notation, but that's okay. Just because it's more difficult doesn't mean it's not worth doing. We've got to say negative infinity to 0. Do I include 0? Should I bracket or parentheses 0? Parentheses, right? And then we've also got between 0 and 1, non-inclusive either, right? And then 1 to infinity. And I guess if we're being really formal about it, I have this in my notes. We've got to put the union symbol in between each one of them as well, right? Maybe it's laziness, but I feel like I get less picky about how we write domains the further and further we go with the course. Okay. I'm going to try to insist on you guys using interval notation whenever we write domains. Okay. All right, let's take a look here. The good old vertical line test, right? We've been learning this since Algebra 1. The easiest way to tell if something is a function or not is using the vertical line test. If it passes the vertical line test, then it is a function. If it does not, then it is not a function. And the reason being is because if you can draw a vertical line, that means one of those x values, wherever that vertical line exists, that x value is going to have 2 different places where it will have a y value. And that's a no-no for a function, right? And that's anywhere. That's anywhere. Like, it could just be in one little spot. Like, for example, if I have something like this, and I go like this, and like that. Is that a function? No. Because this spot right there has 2 values. Everywhere else, it's only got 1 value. But then that has 2 values. That's still not a function. Well, okay, let's modify that a little bit. Is it a function now? Yes, because it jumps down here. We got a discontinuity here. Even though it's a discontinuity, it's still a function because every x value still has a y value, still exists, only 1 y value. And kind of, foreshadowing that is a piecewise function, right? Have you guys worked with piecewise functions before? We kind of skipped that chapter in Algebra 2. Man, you guys are the last class that I had for Algebra 2. Those of you I had for Algebra 2. That was the last time I taught Honors Algebra 2. It's here. I know. Last year I only had Algebra 1 in calculus. Now this year I got Algebra 1 instead. But anyway, we kind of skipped that chapter in Algebra 2. But a piecewise function is just one where it has different pieces and parts to it, right? That's where it gets its name. The functions in the following 4 examples are defined by different formulas in different parts of their domain. When you got each different piece of the domain having a different formula to it, that is what's called a piecewise function. So here's an example of a piecewise function. This is what it looks like in equation form. A function f is defined by, okay, we got 2 different pieces. 2 different pieces of my domain. If it's less than or equal to -1, so say -2, -3, -4, -5. So less than or equal to -1, then I use the rule 1 minus x. If it's anything bigger than -1, 0 or 1 or 2 or 3, then we use the function rule x squared. So all we're going to do here is evaluate f of -2, f of -1, and f of 0, and then we'll sketch the graph. Okay, let's first start off by evaluating f of -2. Okay, f of -2, what rule do I use? The 1 minus x or the x squared? What rule do I use? The 1 minus x, right? Because -2 is less than or equal to -1. I look here in my domain. Where does it fall? It falls within the domain of less than or equal to -1. So I use the 1 minus x rule, right? 1 minus a -2. So 1 minus -2 is obviously 3. And then we find f of -1. Well, because the or equal to is on -1 is on the 1 minus x, I want to use the 1 minus x rule for this as well. So 1 minus a -1, 1 plus 1 is 2. And then we take f of 0. f of 0. Okay, what am I going to use now? Am I going to use the 1 minus x or the x squared? The x squared, because 0 is bigger than negative 1. So we say 0 squared is 0. Now I've kind of just made a little table of values, right? Negative 2, comma 3, negative 1, comma 2, 0, comma 0. That doesn't give me the full and complete picture of the graph, but at least, oh, I forgot again to get a coordinate plane. Got to do that. Sorry, I'm gonna just make one up here. I could go, I want to go to negative 2. Okay, we'll just go up to 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And if I go 2, it's going to be 4, 4, 4, 4, 4. Okay. Okay. Let's plot these points. Yes?
Doesn't 0 squared equal 1?
No. That you're thinking something to the 0 power.
Oh.
That's what you're thinking.
Okay.
Yeah. Let's plot these points first off. I'll delete that from the recording. Negative 2, comma 3. Negative 2, comma 1, 2, 3. Negative 1, comma 2. 0, comma 0. You know, you might be tempted to just like draw a line in between that, right? But that's not actually what happens. Just because these three values tend to make it look like it's almost this linear thing, draw a line through it, that's not what happens at all. In a piecewise function, there's a breaking point in there. There is a breaking point. Where is the breaking point? Where the domain flips. So I like to put in a dotted line. I'll erase that away when I'm all done, but that's my barrier. And I put that dotted line where the domain changes. Or sorry, where the domain, where that threshold is. Now, to the left of negative 1, it is that linear function 1 minus x, right? So it is a straight line from here onward. There is a straight line there. But there is not a straight line from that point on the dotted line down to 0, 0. What would I get if I plugged in negative 1 into the bottom rule? What is negative 1 squared? Positive 1, right? There is actually an open circle here. And you know what? Let me put it blue again. Open circle here at 1, 1. Why is there an open circle there? Because every point to the right of negative 1 exists on that parabola x squared. Like if I were to calculate negative 0.9, right? Negative 0.9. That exists on the right side of negative 1. So it'd be negative 0.9, comma 0.81. And I could calculate everything in between negative 1 and 0. So it exists there just all the way up until negative 1. At negative 1, it flips back over to 1 minus x. And then on the right side, I just got to finish out my parabola on the right side. 1, comma 1, 2, comma 1, 2, 3, 4. Put a dot out there. So it looks parabolic on the right side. Mr. Lippy.
Hello.
How's it going?
Well, walking by, I saw a lot of people paying close attention. So it was difficult.
CCP calculus. Just some review, though. Just talking about piecewise functions. So again, in any piecewise function, you look for where the domain flips. Look for where that threshold is. And I guess if we're formal about it, there should not really be that dotted line in there. I mean, we don't want it to make it look like any sort of inequality or anything. So that should go away in the end. But for your visual purposes, it might be a good idea to draw that in and say, okay, there's my threshold. There's where I have to stop being one function and be the other. Okay. All right, sketch the graph of the absolute value function. F of x is equal to the absolute value of x. Now, the absolute value function is a very unique function. We're going to talk about that. We're going to have a special rule for the absolute value function and just pretty much everything that we cover. If we talk about derivatives, it's going to be weird for the absolute value function. We talk about continuity, it's going to be weird for the absolute value function. Absolute value is just its own weird function. I don't mean to offend, but yeah. So f of x is equal to the absolute value of x. What is the shape of the absolute value function? What is the shape? It's a V shape, right? And why is it a V shape? Well, because if I plug in 0, it's going to stay 0. If I plug in 1, it's going to be 1. Positive 1, 1. Positive 2, 2. Positive 3, positive 3. So it's linear on the right side. And then on the left side, it just takes off the negative. So if I input negative 1, it turns positive 1. If I input negative 2, it's positive 2. If I put negative 3, it's positive 3, right? It's that linear shape just reflected over to the other side. It's not a rounded out bottom, right? It comes to a nice clean corner. It doesn't gradually change over to the other side, does it? Let's make a piecewise function for the absolute value. Okay? Let's make a piecewise function for the absolute value function. Because it has these two separate pieces going on, right? There's the right side, and then the right side looks completely different from the left side. So let's say a piecewise, let's figure out what a piecewise function would be for the absolute value. Where does it break? Where does it change from looking something to looking like something else?
0, 0.
At 0, right? At the x value 0. So we're going to have some rule for when, we should write the word if x is less than 0. And then we're going to have another rule if x is greater than 0. And we should put the equal to on at least one of the at just one of the points. If x is less than or equal to 0, or if x is greater than 0. It doesn't matter where because it connects there. Mr. Lippy used to be a math teacher. Do you guys know him? He likes to pop in. All right, so we have one rule if x is less than 0 and one rule if x is greater than 0. Okay, if x is less than 0, actually, let's go to the easier one first. If x is greater than 0, what happens to a positive number with an absolute value? Stays the same. The input is x, the output is x, right? 1, 1, 2, 2, 3, 3, 4, 4, right? Input equals output. So what's the rule for if x is less than or equal to 0? So if I plug in negative 1, what do I have to do to it to come out right? Make it positive, which means, but we can't define it using the absolute value. Negative x, good, negative x. You might be thinking, well, wait, that's not the rule for positive numbers. You're right, I don't worry about positive numbers there. You know, if I just graphed negative x, you know what it looks like? That, which makes sense because I really only want that. I don't care what's happening down here. I only care about what's happening on the left side because that's the only, I wanted to make a rule for just that side. Okay. So that's the absolute value function written as a piecewise function. Okay. Let's talk about symmetries now. Did you guys talk about symmetries in pre-calc? Even symmetry, odd symmetry? Maybe a little bit. We're going to talk about even and odd functions a lot. Because they have similar, like if we know a function is even, we can do certain things with it. If we know a function is odd, then we can, it like fits a role. They all kind of follow the same rules. Okay, so let's talk about even symmetry. If a function f satisfies this statement, f of negative x is equivalent to f of x. What's that mean? That means that if I plug in an x value, it's the same as if I plugged in negative x, right? It comes out the exact same for every number x in its domain. If that happens, then it's even. The best example I can give you is just x squared, right? What happens if I plug in negative x? Well, the negative gets squared out, so it just becomes x squared, which is the same as f of x, right? If I plug in f of negative x, it turns into x squared. If I just say f of x, that's also x squared. If f of negative x is equivalent to f of x, then it has an even symmetry. Even symmetries are very clear to see on a graph because they're just a reflection over the y-axis. You know, think about the basic parabola, the parent parabola, that just reflected over the y-axis. Is the absolute value even symmetry? Yes, because it's a reflection over the y-axis. Also because if I plug in f of negative x, it's the same as f of x, right? F of negative x is f of x in the opposite value. Okay, what about odd functions? Odd functions, it has to satisfy this rule. F of negative x is negative f of x. So basically, if I take f of x, the function, and I put a negative out front, whatever that means in terms of the function, you know, if it's polynomial, that means I'm going to have everything is negative, right? If it's rational, if it's a fraction, the negative has to come all the way out front of the fraction. Whatever that means in terms of the function, I could pull out the negative all the way out front, and then it would be the same as if I had plugged in f of negative x. Easiest one to see here, right? Easiest one to see here is x to the third. Negative x to the third would be negative x to the third. Negative x to the third is the same as negative x to the third. So this is really equivalent to that. Negative x cubed, that negative can come all the way out in front. So negative x cubed. You know, it sounds like I'm saying the same thing, but there's pauses in there. Okay. So let's determine whether the functions are even, odd, or neither. Corbin, right? Yeah. All right. So to test whether it's even, odd, or neither, you just simply plug in negative x. Let's plug in negative x. So f of negative x. And then we'll kind of see what happens to it to determine whether it's even or odd. And if it's neither, just write neither. Okay, so that would mean in this case I've got a negative x to the fifth plus a negative x. Anything raised to an odd power with a negative, that negative just sits out in front, right? So f of negative x is negative x to the fifth minus x. I can pull out that negative. I can factor out that negative so it looks like this. And what is x to the fifth plus x? Isn't x to the fifth plus x f of x? So I just, that's like an algebraic proof right there. Negative f of x. So I just proved that that is odd. F of negative x is negative f of x. I got potential spam call. Make sure I pick that. I want to get done with this. Oh, so I forgot. Odd. There's my final statement. Okay, let's take a look at our second one, g of x. So I'm going to find g of negative x and just see what happens to it, which is 1 minus negative x to the fourth. Now, what happens with any even power? The negative goes away. So we have g of negative x is really just 1 minus x to the fourth. Okay, so, oops, I forgot to say this. I plugged in a negative, right? So we just showed that g of negative x, come on now, g of negative x turns out to be the same as g of x, because look here. G of negative x ends up being equivalent to g of x. That means even. I'm guessing the last one is neither. One of each, I guess. Let's check. Let's see h of negative x. Okay, so that would be 2 times negative x minus negative x squared. So this becomes negative 2x minus, and then the negative x gets, the negative gets canceled out because of the squared. Okay, as it sits right now, is h of negative x, did that come out to be h of x? No. There's a negative sitting out in front of the 2. So it's not the same. So I know at this point it's not even. Let's try to make it odd. Let's pull out that negative and see if maybe it's negative all of that. So if I factor out a negative, that's going to be a 2x plus x squared. Is this the same as this? No. So it's not even nor odd. It's neither. So just plug in negative x to test to see whether it's even or odd. If you get the exact same thing back out again as your original function, then it's even. If you get the exact opposite of the function, then it's odd. If you don't get anything, it's neither. This looks like our last time. Do I have anything to say about this? Or do I just talk about it? There's no examples of this, but we are going to talk a lot about increasing and decreasing in terms of what's happening at certain times within a function. The graph shown in figure 22 rises from A to B, falls from B to C, and rises again from C to D. The function f is said to be increasing on the interval A to B, decreasing on the interval B to C, and increasing again on C to D. Notice that if x1 and x2 are any two numbers between A and B, oh yeah, that's here's what the gist of increasing versus decreasing. And you're always looking at from left to right. Okay, you're always looking at from left to right. If my endpoint on my left is lower than my endpoint on the right, for all points in between those two pieces, then you know it's going to be increasing. If my endpoint on my right is lower than my left endpoint, then I know it's going to be decreasing. If it's going up the roller coaster hill, then it's increasing. If it's going down, then it's decreasing. So this one goes increase, 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 decrease, decrease, increase, increase, right? And we can describe that within interval notation too. So I can say, when is this function increasing? If I were given values, I say, okay, well, I could just use A and B. Interval from A to B is increasing. Interval from C to D is increasing. So they are both they're increasing on both intervals there. And it is decreasing from the interval B to C. Okay. All right. That is it for section 1.1. Let me stop the video.